Imagine your application is scaling beautifully. Users are signing up, traffic is growing, and then everything stops. Your Postgres logs are filled with remaining connection slots are reserved. Or worse, the database just becomes unresponsive. You check the dashboard and see exactly 100 active connections. Why does a powerful database engine struggle with a number that seems so small? In this video, we'll explore why Postgres uses a process per connection model, the hidden cost of context switching, and how connection pooling saves your production environment from total collapse. Understanding this bottleneck is the difference between a system that scales linearly and one that hits a hard ceiling at the worst possible moment. Let's look at what's happening under the hood when a new client says hello to your database.
Unlike some modern databases that use lightweight threads, Postgres uses a process-based architecture. Every time a client connects, the postmaster process forks a completely new backend process. This design is robust and provides great isolation. If one backend crashes, it doesn't take down the whole system. However, this isolation comes at a price. Each process requires its own memory space for things like sort buffers and hash tables. Even an idle connection consumes several megabytes of RAM. When you have 10 connections, it's negligible. At 100, you're looking at hundreds of megabytes of overhead just to maintain the pipes before a single query is even executed. This fork-heavy approach was a brilliant design choice for reliability in the 90s, but it creates a specific scaling profile that modern web apps often ignore until it's too late.
It's not just about memory. It's about the effort of creation. Forking a process is a relatively heavy operating system operation. The OS has to copy page tables and set up a new execution context. If your application creates a new connection for every single HTTP request, a common pattern in serverless or poorly configured ORMs, your database spends more time birthing and killing processes than actually searching for data. This is why connection latency becomes a dominant part of your response time. Beyond the initial setup, there's the ongoing management. The operating system scheduler now has to juggle 100 competing processes, all fighting for the same CPU cores. As we'll see next, this competition leads to a phenomenon called thrashing, where the CPU spends more time switching between tasks than actually finishing them.
When the number of active processes significantly exceeds the number of CPU cores, performance doesn't just plateau, it drops off a cliff. This is context switching. To give every connection a fair slice of time, the CPU must constantly save the state of one process and load another. This involves clearing caches and updating registers. At high concurrency, your CPU cores are working at 100% utilization, but your query throughput is actually decreasing. It's like a kitchen with 50 chefs and only 4 stoves. They spend all their time bumping into each other rather than cooking. This is why Postgres performance often peaks at a connection count roughly equal to 2 or 3 times your CPU core count. Anything beyond that is usually counterproductive, leading to increased latency for every single user. The solution isn't to buy a bigger server, it's to change the relationship between clients and the database. This is where a connection pooler like PgBouncer or AWS RDS proxy comes in. The pooler sits between your application and Postgres. It maintains a small pool of warm, persistent connections to the database. When a user makes a request, the pooler assigns an existing database connection to that request, then takes it back the moment the work is done. Your application might think it has 1,000 connections, but the database only sees 20. This effectively decouples your logical connections from the physical processes on the server. By keeping the physical connection count low and stable, you eliminate the overhead of forking and the misery of context switching, allowing Postgres to operate at its peak efficiency. Not all pooling is created equal. The most common mode is transaction pooling. In this mode, the pooler gives a connection to a client for the duration of a single database transaction. Once the transaction commits or rolls back, the connection is immediately returned to the pool for someone else to use. This is incredibly efficient for web workloads, where most requests are short-lived. The alternative is session pooling, where a client keeps the connection for as long as they stay connected. While easier to set up, session pooling doesn't solve the scaling problem as effectively. With transaction pooling, you can easily support thousands of application users with just a few dozen database connections. However, you must be careful. Certain features like prepared statements or session-level variables can break in transaction mode because the next transaction might happen on a completely different physical connection. So, how do you fix your crashing database? First, audit your connection strings. If you're using a serverless platform like Vercel or Lambda, a pooler is mandatory because these environments spawn hundreds of short-lived instances. Second, size your pool correctly. A good rule of thumb is your pool size should be 2 times your CPU cores plus your effective spindle count. Usually, a pool of 20 to 50 is plenty for even high-traffic sites. Finally, monitor your waiting clients metric in PgBouncer. If clients are waiting, it means your pool is too small. If your CPU is pegged but the pool is full, your queries are too slow. By moving the connection management logic out of the database and into a dedicated proxy, you transform Postgres from a fragile bottleneck into a resilient, high-performance engine.